The University of Michigan AI Laboratory has developed a comprehensive evaluation framework for AI systems operating in the wild, as outlined in this white paper. This framework focuses on assessing generative AI and other AI technologies beyond controlled lab settings, emphasizing real-world performance, safety, and ethical considerations. Key takeaways from the paper highlight the need for dynamic, multifaceted evaluations that go beyond traditional benchmarks. It stresses the importance of involving diverse stakeholders, including human evaluators, to ensure AI systems align with human values and societal needs while addressing limitations in current methods. In the executive summary, the authors, led by senior contributors like Michael Wellman, Brian Goodman, and others, with corresponding authors David Jurgens and Lu Wang, present an overview of the challenges in evaluating AI systems. They argue that standard lab-based tests often fail to capture how AI behaves in unpredictable real-world environments, such as everyday applications or high-stakes fields like healthcare. The introduction to GenAI evaluation delves into the evolution of AI assessment. It explains that generative AI, which creates content like text or images, requires evaluations that account for creativity, accuracy, and potential biases. The paper critiques existing evaluation methods and their limitations, noting that many rely on static datasets or simplified metrics that don't reflect the complexity of real-world interactions. For instance, these methods might overlook edge cases, cultural variations, or long-term impacts, leading to over-optimistic or incomplete assessments. When considering what is being evaluated, the paper categorizes approaches into three main types. First, in the lab evaluation involves controlled experiments where AI is tested in isolated environments with predefined inputs and outputs. This method is useful for initial debugging and measuring basic performance metrics like accuracy or speed, but it often lacks external validity. Second, human capability-specific evaluation focuses on how well AI mimics or augments human skills. For example, it might assess an AI's ability to understand language, generate coherent responses, or perform tasks like summarization. The paper points out that this type of evaluation requires metrics that align with human judgment, such as fluency, relevance, and empathy, to ensure the AI is not just technically proficient but also practically useful. Third, in the wild evaluation examines AI performance in real-world scenarios, where variables like user behavior, environmental factors, and unexpected inputs come into play. This is crucial for systems deployed in everyday use, as it reveals issues like robustness to noise, adaptability to new contexts, or unintended consequences that lab tests might miss. Shifting to who evaluates and how, the paper discusses benchmark-based evaluation, which uses standardized datasets and automated scoring systems for efficiency and scalability. These benchmarks, like those from popular AI challenges, allow for quick comparisons across models but can be rigid and fail to capture nuanced human preferences. In contrast, human-centered ML evaluation incorporates people directly into the process, gathering feedback through user studies, surveys, or expert reviews. This approach ensures evaluations reflect diverse perspectives, but it involves trade-offs between automated and human-centered methods. Automated evaluations are faster and less expensive, yet they may lack depth and introduce biases from the algorithms used. Human-centered methods, while more insightful, can be time-consuming, subjective, and resource-intensive. The paper also explores the roles and expertise of stakeholders in human-centered evaluation. It suggests involving a mix of domain experts, end users, ethicists, and AI developers to cover technical, social, and ethical angles. For instance, in healthcare AI, clinicians might evaluate accuracy, while patients provide input on usability and trust. Another innovative aspect is the use of large language models, or LLMs, as judges. The paper proposes leveraging advanced AI models to automate parts of the evaluation process, such as scoring generated content or detecting hallucinations. However, it cautions that LLMs themselves can inherit biases, so their role should be supplementary to human oversight. Other considerations in the framework include the balance between objective and subjective evaluation. Objective metrics, like error rates, are quantifiable and reproducible, but they may not align with human perspectives, values, or ethical standards. Subjective evaluations, based on user ratings or qualitative analysis, help bridge this gap by incorporating cultural, moral, and contextual factors. Safety-focused approaches are emphasized as essential, particularly for high-risk applications. The paper advocates for evaluations that assess potential harms, such as misinformation, privacy breaches, or discriminatory outcomes, using techniques like red teaming or stress testing AI in adversarial scenarios. Practical systems evaluation is another key area. For ML training, the framework calls for holistic assessments that consider not just model accuracy but also the entire system, including data pipelines, infrastructure, and integration. When evaluating deployed GenAI systems, it recommends monitoring real-time performance, user interactions, and system updates to adapt to evolving conditions. The paper also addresses power, energy, and sustainability considerations in AI evaluation. It highlights the environmental impact of training large models, urging evaluators to measure energy consumption, carbon footprints, and resource efficiency as standard metrics. This is increasingly important as AI scales up, potentially exacerbating global sustainability challenges. Additionally, it differentiates between data processing or selection and model performance. Poor data choices can undermine even the best models, so evaluations should scrutinize data quality, diversity, and sourcing to ensure fairness and representativeness. On the topic of how long evaluations remain relevant, the paper introduces the concept of dynamic evaluation and benchmark automation. Traditional evaluations can become outdated quickly due to rapid AI advancements, so the framework promotes ongoing, adaptive assessments. This includes automating benchmarks to run continuously, allowing for real-time monitoring and updates as new data or threats emerge. Evaluating the evaluations themselves is a meta-level consideration. The paper stresses the need to assess the validity, reliability, and biases of evaluation methods, ensuring they are transparent, reproducible, and inclusive. Finally, the paper presents case studies to illustrate these concepts. In the health AI example, specifically clinical note summarization, what is being evaluated includes the AI's accuracy in condensing medical records, its ability to preserve critical information, and its potential for errors that could affect patient care. Who should evaluate involves a multidisciplinary team: doctors for clinical accuracy, patients for comprehensibility, and ethicists for privacy and bias concerns. How long the evaluation should last depends on the context, with ongoing monitoring recommended to account for changes in medical practices, data updates, or AI improvements, ensuring sustained safety and effectiveness over time.